Hi, welcome back to the course Computer Vision from Scratch. In this lecture, we will be building our first neural network for performing image classification. This will not be an extraordinary neural network. This will be the simplest neural network that you can ever imagine. It has three properties. It will be shallow, so it won't have deep hidden layers. I'll tell you exactly what this means. Then it will not have any activation function. So this will be a linear neural network. And finally, this neural network will not have any convolution operation. So it's a very straightforward, simple neural network. And what we are going to explore in this lecture is, can this neural network perform a decent image classification, or will this be exceptionally bad? So let's see that through this lecture. And this lecture will answer many questions for you. It will make you understand how the neural networks work, how it does image classification, the effect of depth of neural network, the reason why we may have to do convolution operation, etc. So this lecture is a package where you will have a deep understanding of how, in a very basic sense, image classification works with very simple neural network. So before getting into the lecture, I want to spend just 1 minute mentioning something that we have been mentioning throughout this course. That is, many students start courses, but they don't finish them. So most, I would say 95% of the students belong to this bucket, where there are large number of people who start a course, but if there are 30-35 lectures, gradually they will lose motivation, and maybe 5% or less than 5% students actually end up finishing the last part of the course. So if you have started this course, if you have reached till this point, it means there is a reason why you have started, right? Because you are serious about learning computer vision. So just remember that you have like a mission going on here, and your mission is to finish this course and learn in depth the concepts behind computer vision and help it advance your career or whatever you want to do with it. So let's take a small pledge that we will complete this course which we have started. And to keep you accountable, feel free to put a comment saying lecture 3 finished after this lecture, or find a friend who can keep you accountable. So keep each other accountable, so that there is great motivation for you to go lecture after lecture. So with that, let us get into today's lecture. So as I mentioned, we will be building a shallow neural network. What does shallow neural network mean? You will see soon. And this will have no activation function. And this has profound implications on what this neural network can or cannot do. Then at the end of this lecture, you will have a fairly good idea about neural network architecture, operations like flattening, softmax, operations like terms like fully connected layers, the idea behind activation function, the idea of deep neural network, and also the need for the famous convolution operation, which is used in convolutional neural networks. So we will explore all these concepts in today's lecture, along with building the neural network ourselves. So firstly, the difference between deep versus shallow neural network. In a shallow neural network, there will be only one hidden layer. So input layer converted to one hidden layer, and that is converted to output. In deep neural network, there will be multiple hidden layers, and these hidden layers help us transform the input features into different transformed features. And then finally, that can be converted into some output prediction. So this is the fundamental difference between shallow and deep neural network. And as you know, most of the modern machine learning, computer vision approaches rely on deep neural networks, not on shallow neural network. But before we venture into building deep neural networks, we will start with shallow neural networks. So we know that our fundamentals are very clear. So with that, let's first discuss what dataset are we going to be using. So this dataset is called 5 flowers dataset. It has 5 category of flowers: daisy, dandelion, roses, sunflowers, and tulips. And each flower category here in this dataset has 1,000 images, and these images are in JPEG format. So totally there are 5,000 images, and each class in these 5 category of flowers have 1,000 images each. Okay. This is a famous dataset, by the way. It's openly available. You can find it on Kaggle. You can find it from this GitHub repository as well. And this dataset is also the basic dataset that is used in this famous book, Practical Machine Learning for Computer Vision, published by O'Reilly. So as I mentioned in the very first lecture of this course, we'll be following the structure that is followed in this book as well. But all of these resources, the GitHub repository, the data set, everything is publicly available. So I will be sharing the link to these, the code that I'll be writing, plus the GitHub repository and where you can find the image data set, etc. Everything I'll be sharing with you. Now, the first step is, okay, we have the data set somewhere. Maybe it is on the internet, maybe it's on our local computer, maybe it's on our personal Google Drive. But we have to read the data set, right? So the first task is loading the file. The files are all in JPEG format, but we won't be using the JPEG files directly in our machine learning, or in the neural network model that we are building. But rather, we'll be first converting this JPEG format into RGB values. So as you know, red, green, and blue channels are existing in any normal image. So any image you can consider as a collection of 3 matrices. One of those matrix, let's say it's a 32 by 32 image. So one of the matrices will be just about the intensity of each pixel in terms of a red color channel. Then there will be another matrix which corresponds to green. Then there will be another matrix which corresponds to blue. And if you combine all these 3 into one single image, that is what you see. But we have to first convert the JPEG into corresponding RGB matrix value so that we have numbers. We have the image represented in terms of the numbers. And these numbers are pixel values, which range from 0 to 255 normally. So 0 means it will be black. 255 means it will be bright. Now, if we are talking about 0 to 255 for red channel, 255 means it will be completely red. 0 means there will be no color. It will be completely black. Now, what we do is we will scale down these values. Instead of it being from 0 to 255, we'll scale it down to 0 to 1. And then one more thing that we'll do is we'll resize all images to this dimension, 224 by 224 by 3. 224 by 224 is the resolution of the image, and by 3 because you have 3 channels, red, green, and blue. And why are we performing this resizing? Because the input data set for any machine learning model, for example, if it's a neural network based model that you are trying to build, the input data set, which is images, may contain images of various sizes. Maybe the photographer who took one image and the photographer who took another image used different camera settings or different cameras. Many things can change. But the problem is, if these images are of different sizes, the number of pixels present in these images will vary, which means if you are inputting this image into a neural network, the input dimension will be different, and that is not good. You want the input dimension for all data points to be exactly the same when you're inputting something to neural network. So first you will be resizing the image such that all the images which we are going to be using for training or for validation in this example will be of the dimension 224 by 224 by 3. So one more thing is, once we have loaded these images or once we have read the images, we want to ensure that the images are actually in a good shape, meaning they are accidentally not flipped or they are not accidentally upside down or something. So we can't obviously manually check all the images, but it is very crucial to verify that at least the data set that you have read is kind of sane. It's not completely random, or it's not a completely different data set. So some sanity check you have to do. And this you can do by simply visualizing a few images. So you visualize some images of the flowers to see that you indeed have the flower data set and the data set has no issues, like it's working, there is no corrupted file or anything. And you don't have to check this for every single file, but at least check it for a few number of images. So we will be also doing this. So before getting into the coding part of this, and we'll be coding today purely in Google Colab, so that you don't have to pre-install anything. It's very easy to do. You don't need to install separately Python. Everything is running on Google's server. There are three Python libraries that we will be using today. One is TensorFlow, one is NumPy, and one is Matplotlib. So I want to take a small deviation to explain these three libraries very quickly. I won't take too much time before going to write the code. So these three libraries you will encounter multiple number of times throughout the rest of the course. So what do these libraries do? So TensorFlow is developed by Google. It's a deep learning framework meant for building training neural networks for machine learning, deep learning applications. The good thing about TensorFlow is that it supports GPU as well. So GPU means graphical processing unit, like what NVIDIA is selling these days to all the AI companies. Basically, it allows you to perform calculations, mathematical calculations that involves matrices very fast. So this increases the speed of your training or speed of your inference. NumPy is for numerical computing in Python. So this allows you to deal with n-dimensional arrays, ND array, and NumPy is a framework which will also allow you to do vectorized calculation than traditional Python list. So a traditional Python list is something like a equal to 1, 2, 3. This is a list. And in traditional Python, basically the way you represent a matrix, so let's say you have a 2 by 2 matrix, it is represented as a list of list. So this is a 2 by 2. This is in effect a 2 by 2 matrix. This is a list of list because it's a list, first of all, because it's enclosed in the square bracket. It's a list of lists because inside the list, there are two more lists. This is one list and this is another list. And this is how traditionally matrices could be represented in Python, but NumPy makes it even better if you especially want to perform calculations like matrix multiplication. Matplotlib is a data visualization library for plotting graphs, charts, etc. So these three we'll be using. And in fact, you'll be using these three almost always when you are working on deep learning. There is one more key difference between NumPy and TensorFlow that you should know. One is in TensorFlow, we represent the same thing that we represent as arrays in NumPy as tensors. And NumPy typically uses CPU. So it's much more efficient than just traditional Python lists or list of lists. But NumPy relies on CPU. However, TensorFlow can use GPU if a GPU is available, which is much faster than CPU. So for large scale computations, like if you are multiplying a 10,000 by 10,000 dimension matrix, then you will see that using TensorFlow is significantly better than just using NumPy. So I have written a code here. I don't want you to do anything with this code, but basically I want to run the code and show you the difference between NumPy and TensorFlow in just less than a minute. So first, let us open Google Colab. So colab.research.google.com, and I'm going to copy this code. I'll explain it briefly, but I'm not going to go through this particular code line by line because it's not our primary goal in this lecture, but this is just a demonstration of TensorFlow versus NumPy. So once the Colab opens, first what we will do is we will not connect with GPU. We will just use CPU, right? So we paste the code, then we can name this as TensorFlow versus NumPy, NP, and we can connect to some runtime. So this will be here, you will see a connect option and it will be by default connected to Python. So on Google Colab, you can run Python, R, or Julia. So here, first, let us try multiplying two matrices of dimension 100 by 100. Not too big. So 100 by 100 is not a very big matrix when you compare with the kind of matrices that are usually dealt with in deep learning. So here, this will finally print the matrix multiplication time it took using NumPy and using TensorFlow. So we are defining a matrix A as random numbers of dimension 100 by 100. We are defining a matrix B of dimension 100 by 100, again of random numbers. Then this A, which is NumPy, and this is also NumPy, we convert into TensorFlow format. That is ATF and BTF. Then what we do is we say C NumPy is the matrix product of A and B, whereas C TensorFlow is the matrix multiplication using matmul for A and B. So here you can see that NumPy actually did it fast, 0.004, whereas TensorFlow is actually a bit slow, 0.08, because here we are trying to see if GPU is available, it will be using GPU. But the difference mostly comes when you go to larger and larger matrices. So this is n equal to 1000. And here now you can see that NumPy is taking slightly more time, 0.06, and TensorFlow is taking 0.062. This is 0.066. And if I make this into a matrix of dimension 10,000, it will take overall more time. Both of them will take more time, but hopefully you will see that NumPy matrix multiplication takes more time than TensorFlow matrix multiplication. We don't have GPU yet. I don't think my computer has GPU access. So I think both of these are still done on CPU. So here, although I have written on GPU, it will be used only if it's available, only if GPU is available. So this will take around 10-15 seconds to execute. I have tried this before, and let's wait until this is finished. So here the execution has finished. It took slightly more than 1 minute. NumPy took 68 seconds. TensorFlow took 39 seconds. So here, although I am printing that this is GPU, actually this is only CPU because I haven't activated GPU yet. So now what we can do is click here and change runtime type and select T4 GPU. Okay, this is freely available on Google Colab. Select T4 GPU. Which means you will be getting access to the GPUs which Google has, and then we can run the same code. And I want you to take note of the time it takes to execute the NumPy matrix multiplication this time, especially. Okay, so let's run this. Hopefully it should run faster. Let's see. So we have the results. NumPy matrix multiplication this time took 48 seconds. Before it was 68 seconds. So similar order of magnitude. But look at TensorFlow, 0.14 seconds. Previously, how much was it? It was around 39 seconds. So it is almost 2 orders of magnitudes faster with GPU. And this is possible only for TensorFlow. So the takeaway here is that whenever possible, convert your NumPy matrices into TensorFlow format so that you can execute things faster. If TensorFlow representation is possible, and which means if GPU is available, TensorFlow will automatically make the calculation using GPU. So this Google Colab file I will share with you, and try playing with it and try playing with this dimension of the matrix, and you will see that the bigger the dimension, the bigger the difference between the bigger the difference in speed between execution using NumPy and TensorFlow. Now let's come back to the thing that we were trying to do, reading the image dataset. So there are a few steps involved. Firstly, the information about these images are present in a CSV file, which we will access through a particular URL. So through this CSV file, we will read the images, and then we will convert the images into TensorFlow dataset. Then we will create batches of images so that we can process, meaning we can train the neural network by sending batches of images parallelly. So training can be faster. So here, what we mean by batch is a collection of 16 or 32 images. So the batch size can be pretty much anything, but there are certain thumb rules for what the batch size should be. In our case, we'll be using a batch size of 16 images. So we'll be processing images 16 images at once. And then we can also visualize a single image example. So here in this step, we are not yet training the neural network because we have not defined the neural network at all in the first place. We are simply just reading the data. We are creating a code which will allow us to create batches of images. Then from a particular batch, we will just visualize some individual images just for the sanity check. So these are the only 3 things we are doing right now before we even start building the linear neural network. So the first step is loading the CSV file, reading the images, and creating the TensorFlow dataset, right? So let's go to Google Colab, click File, new notebook in Drive, and this we can name as first linear neural network. So for image processing. So let that load. I'll name this as linear neural network for images. Okay. So now let us look at the code first. Obviously, we are importing TensorFlow. So import TensorFlow as TF. TF is the short form for TensorFlow. As TF. Then we are defining a few parameters here, I mean constants here: image height, image width, image channels. So 224 pixels by 224 pixels by 3 channels for RGB. So this we will be using throughout. So we are defining it as sort of like global variables. Then we have 5 classes, right? So we have 5 image flower categories: daisy, dandelion, roses, sunflowers, and tulips. So that's what we are defining here. So we can run this code. Nothing special will happen because we are simply defining variables. So there will be no output or anything to expect from this, but just run this code. Fairly easy. Okay. Now, after this, we are writing a function called read and decode. In the read and decode, we are performing the following operation. So first is, into this function, we'll be passing the file name and the dimension to which we want to resize the image. And what is that dimension? That should be 224 by 224. And there are 3 channels. So now we use TensorFlow tf.io input output read file. So this will read the file, but the images are still in the JPEG format. And then we will convert the image into pixel values from 0 to 255 using this. And then we will scale down the pixel values from 0 to 1 instead of 0 to 255 using this line of code. And then we will resize the image. So all of these are predefined functions inside the TensorFlow. That is why TensorFlow is so useful. This decode JPEG, convert image data type, image.resize. All of these are functions already pre-built in TF in TensorFlow. And last one is resize. So resize dimensions means it will resize to 224 by 224 by 3. And then this resized pre-processed image will be returned to wherever this function called read and decode was called from. Now, first of all, we have to see what is this file name. Resize dimension we already know, but we don't know what the file name is. So let us check where we are using that. We have one more function called parse CSV line. So here is where we be reading the CSV file that I mentioned earlier. And then from that, we will be getting the specifications of the image. So firstly, we are reading 2 columns that are present in the CSV file. So that is why I have mentioned these 2: record default as empty. So basically, we'll be reading 2 columns, whatever is the default title of those columns are. And then tf.io.decode CSV, this function will fetch the file name, the image name, and the image label. So label is one of the 5 classes which we mentioned above here. This one: daisy, dandelion, roses, sunflowers, and tulips. And then what we have to do is we have to map the class names to the label string, right? Because label string would be maybe all of them are small letters instead of capital letters. Maybe there is a difference in the way label string is defined and the class name is defined. So here what we are going to do is we are converting the label string integer into the index of the class name. So index of the class name meaning here the index of daisy is 0. Index of this is 0, 1, 2, 3, 4, right? So if a daisy is present as the class name in this label string, then that value will be converted to 0. If it is roses, it will be converted to 2, like that for all images. So basically here the label string, which is a string, is converted into an integer from 0 to 4. And then we are returning the images and the corresponding labels. Labels meaning a string an integer from 0 to 4. Now, this is where we define the training dataset and the validation dataset. So training dataset we will be using in training the linear neural network model. Validation dataset will not be exposed to the neural network model until we are testing it. So we will not be using this for training. And here there are 2 separate Google Cloud CSV file URLs that we can provide. So directly this tf.data.textline dataset basically fetches the metadata about the link to the file, the name of the file, the corresponding flower name, which is the label, etc. So, and then here we are defining this as batches of 16 images. So training dataset, the total number of dataset will be divided into batches of images where every batch has 16 images like that. So you can actually try with 8, 32, etc. And see what is the effect of that on classification accuracy. So this batch size is in fact called as one of the hyperparameters. So you don't know what is the ideal batch size to use. It will evolve as part of your hyperparameter tuning, which you usually do when you are training or building a neural network. So this is all the code. So let us actually execute the code one by one. So first we can define the read and decode function. So let's copy this and paste it in a new code block. So here we will be reading. This function will not do anything yet because we are just defining it. We have not called it yet. So let us now copy and paste the parse CSV line. So here the CSV that we'll be passing into this parse CSV line function will be decoded into the file name, meaning the image data and the image label. Then the next one is defining the training data set and the testing data, validation data set. So let us run this. So now when we run this train data set, we are calling the parse CSV line function, which is this. Parse CSV line function is calling the read and decode function, which is this. Into the read and decode, we are passing the file name and we are passing the resize dimension. And resize dimensions is this image height and image width. What was this? 224 by 224. And then whatever this is returning. So the read and decode function will return image that is converted into scaled format, 0 to 1 scaling plus resizing into 224 by 224. So that will be stored here. And the corresponding label will be obtained from the label string. Label string is taken from the CSV line. CSV line is obtained from the CSV train.csv train set.csv that we are reading here, right? So parse CSV line will get access to CSV line. CSV line is basically the corresponding to the train set CSV. And then from that, we will read the file name and label string. File name is converted into image, which is the pre-processed image. And the label string is converted into a label integer, which is this label. So finally, we have the pre-processed image, which is scaled down and cropped into 224 by 224 by 3. And label is a number between 0 to 4. It can also be a one-hot labeling. So it depends on what you want the formatting of this label to be, right? Okay, so now let us run the train dataset and evaluation dataset. So now we have both datasets ready. These codes are executing so fast. Nothing will be visible yet because you are not visualizing anything yet. So next, that is exactly what we are going to do. So we have set up the pipeline, right? So this is the pipeline. So we want to display some random image from a particular batch. So here, this is a code which says, okay, from the train data set, take the first batch. So you have image batch and label batch. Image batch is the 16 images that are present in the first training data set batch. So image batch is for image batch and label batch in this, meaning you are running the for loop 16 times because you have 16 items in the first batch. Then you are printing the shape of the batch, image batch, and shape of the label batch. One minor correction I have made in the previous block of code, which defines the data set, is introducing this tf.data.autotune, which allows the TensorFlow to automatically decide the parallelism in processing the batches. So this block of code, which produces which fetches the data set according to which batch number we are mentioning. This was taking a lot of time to run and eventually it was not running for me. So I just introduced this extra parameter in this dot map function, and I also had this dot prefetch function. So now this is working perfectly. If I run this once again. Okay, let me first run this block of code. So now we get the output, which is the image batch shape. Image batch shape is there are 16 images in the batch. Each image is 224 by 224 by 3. So that is why this shape is 16, 224, 224, 3. And the labels, there are for these 16 images, there are one label each, right? So that is why the shape of this label batch is just 16. And these are the individual labels. So as I mentioned earlier, the labels are from 0 to 4, 0, 1, 2, 3, 4. corresponding to these 5 images, Daisy all the way till Tulips. So here you can see that there are 3 images here, which are Dandelions, and then there are tulips here. There are actually 3 tulips, and you can see that you can see the kind of distribution of these images in this particular batch. If we take another batch, we can see the shape of that also. So here this will print the shape of both batches, first batch and second batch, and you can see that in the second batch there are these kinds of images. If we take the first 3 batches, you will see the kind of labels in the third batch. So you can see that the distribution is fairly good. There are good distribution of all types of flowers in this data set if you just look at these batches. So, okay, so now you know that you have the batches are basically doing what it is supposed to do. Each batch has 16 images and it's 224 by 224 by 3. Now, the last step in the image reading pipeline is just visualizing a single image, right? So for that, we will use this matplotlib function, which we discussed earlier. So within that, we will use matplotlib.pyplot. So here we are fetching one particular image and its corresponding label from the training data set, and then we are just plotting it. So let's do that. So we can copy this code. So this is a fairly simple code. I'm not going to go through it line by line. It's fairly straightforward. So just run the code and see for yourself what it accomplishes. So here, this will print the image at the index 0 in this in this batch, and here it's a Daisy. So this flower is Daisy, and its label is shown above. We can also print an array of maybe 16 images in one batch. So let's see how to do that. So while this is printing the 0th image in the first and second batch, so this is Daisy, this is also Daisy, we can print all the 16 images as subplots in matplotlib. So here we will see that, yeah, these are the images. These are the 16 images in the first batch. So 4 by 4 grid. So Daisy, Dandelion, roses, tulips. See here, look at this image, for example. This is literally, this could have also been a tractor. I did not even notice the tulips. And here sunflowers, but there is a person. So images are of all varieties. See, look at this. This is like an indoor image, not even outdoor. So you can see that images come in all varieties. So here, if we instead put 2, it should show the images in both batches, I suppose. So there should be 32 images here now. Yeah, so the first 16 by 16 grid, this 16 by 16 grid is from the first batch. This 16 by 16 is from the second batch. So here again, I think this person here with sunflowers and this person are probably the same. Roses, Daisy. So all varieties are there. So this is a proof that our image reading pipeline is working, and we are able to fetch the images. We are also able to fetch the labels, corresponding labels, and the labels have been converted into numbers ranging from 0 to 4. So this is very good start. Now we are good to go ahead with the rest of the coding process. So with this individual image visualization and batch visualization, we know that our TensorFlow pipeline for reading and converting images into the specific format that we need is working. Now we can build the neural network, the simple shallow neural network that we discussed earlier. So remember, no activation function, no convolution. Okay. So we have now a very good data set. And we know that linear models are not well suited for doing complex tasks because linear models can only learn linear patterns. So a linear model is what? A model of the form y equal to mx plus c. So if the data set is all aligned along a straight line, then yes, y equal to mx plus c format models are very good. Now, y can be individual number, x can be individual number, or it can be a vector also. So that's what happens here, right? So we are calling the first model that we use here as linear because we are not going to be using any activation function inside the model, right? So, and the question will be here, are we able to build a neural network that can actually perform some meaningful classification? So first of all, let us think about what is a bad model here. a bad neural network in this case will not have 0% classification accuracy, because that is not possible. The worst classification accuracy possible is 20%. Why? Because let's say you are a monkey who's choosing that, oh, this image belongs to roses, this belongs to dandelions, assuming there is equal split of the data set, then a monkey will be correct 1 out of 5 times, right? Because of the random probability. So there is a 20% chance that if you randomly guess what the image belongs to, you will be correct. So the worst classification accuracy that should be possible is 20%. So if the question here is not whether this model is going to give us 0% accuracy or 100% accuracy, the question here is how much better than a random classification, like how much better than 20% can we get with a shallow linear neural network without any convolution operation? That is the question that we are asking ourselves here. So the 3 operations that we'll be performing in the neural network are, first, the image, which is 224 by 224 by 3 pixel images, we'll flatten. Flatten meaning it will look like one single vector as a column. It will not look like 3 matrices or tensors with 3 dimensions. It will look like a flattened vector, like a column. Then we will define a dense fully connected layer, and this layer will be connected to the output, and at the output we will have softmax. Now you will have a very natural question: did I not tell that we are not using any activation function? So why am I suddenly saying softmax here? Isn't softmax also an activation function? I'll come to that in a moment. So firstly, this is the neural network architecture that we'll be building. We have RGB channels of 224 by 224 by 3, because RGB, there are 3 red, green, and blue channels. And then what we are going to do is we will be arranging RGB in the 0th position in each channels as RGB. So these 3 elements which are in 3 dimensions, we linearized into just 1 dimension. Similarly, then we will move to the next one. Then again, there will be another set of RGB. Like that, 224 by 224 by 3 dimension will be converted into one single vector. And what is the dimension of that? 224 into 224 multiplied by 3, that is 150,528. That should be the dimension of this particular layer, which is the input layer of the neural network. Now you can also call this, by the way, as hidden layer, because if this is considered as the input layer, then your input is converted into flattened is converted into output. Now this input to output connection, or this one flattened layer to output connection, is a fully connected connection, meaning every single every single node in this neural network. So these are called nodes. This is a layer. These individual items in this neural network are called nodes. Here also, this is the output layer, and these are nodes: 1 node, 2 node, 3 node. So in the input, there will be 224 by 224 by 3 nodes. In the output, there will be 5 nodes, because we are trying to classify into one of the 5 categories. And here you have fully connected layer. So what that means is every node in this layer will be connected to every other node in the final output layer. There is one more small caveat. Here, the output could be some random numbers. So let's say the image is that of Daisy. This number might be 22. This is minus 0.3. This is 1.7 or 1.3. And this could be 1.9. This could be 14.2. Now, these numbers, we will convert to a probability distribution, where here Daisy has the highest number, meaning this is very likely that this is a Daisy flower, which means if you have 5 bar plots, the bar corresponding to Daisy will be highest, bar corresponding to Tulips will be the second highest, and remaining ones will be very, very small. And the height of these bars, when you add all on one after the other, you will get sum equal to 1. So this operation, which allows you to convert a set of numbers into a probability distribution whose values are greater than 0 but less than 1, and whose sum is equal to 1, is called softmax activation function. So here we are using softmax, but not in the model itself, not in the neural network itself, just to convert the final outputs into probability distribution, right? So we will finally get something like this, a probability distribution for what this image is corresponding to. And if you have a distribution like this, you can say that this image corresponds to whatever this index is. Is 0 means I think it's Daisy. So this is Daisy. So that is the question that I earlier asked. I said that there is no activation function being used. So how come softmax is there? Softmax is, yes, it is an activation function. However, it is not being used in the model. So our final output is of this form. It is y equal to softmax of wx plus b. And what is w and what is x? X is the flattened image data, right? Basically, you have 224 by 224 by 3, that many dimensions. So x is that particular, let's say this number equal to p. X is p by 1 matrix, p by 1 input. W is the weight matrix. So you have weights corresponding to, so let's say this is called as weight 1, 1. This is weight 1, 2, weight 1, 3, like that up to weight P1. Then you will have the next one. So, okay, first, if you are looking at, this will be weight 1P, 1, 1, 1, 2, 1, 3, etc. up to 1P. Then like that, weight 2, 1, 2, 2, 2, 3, 2, 4. Okay, I think I'm not getting it correctly. This is weight 1, 2, weight 1, 3, weight 1, 4, weight 1, 5. Similarly, you have weight 2, 1, 2, 2, 2, 3, 2, 5, like that up to weight P1, P2, P3, P4, P5. So all those weights are there. Then there could be bias. Bias is this B. It is just a number, constant number added to the weight multiplied by input product of each node. So bias can be 0, bias can be a non-zero number. It depends on whether you want to initially introduce bias or not. And this output, whatever we get, could be numbers like this, right? Numbers like 2.22 minus 0.3, whatever. And then you are converting that into a probability distribution using softmax. So this is your neural network. You are not using any non-linear activation function inside this part. It's purely linear of the form y equal to mx plus c. So this is mx and this is like c. Softmax is just for converting your calculation into probability distribution. So this model still cannot learn any non-linear patterns in the data. The internal part where model is calculating an output just before converting that into probability distribution has no non-linearity. So that is why I mentioned that this model is a purely linear model, although softmax is present at the very last step. Okay. Okay. Now what we can do is we can define this linear model using Keras. Keras is a library in Python which allows you to make TensorFlow usage a little bit easier. So here, what is done is you are importing from TensorFlow, you're importing Keras, and then Keras allow you to define the neural network with layer by layer sequence. So here, Keras.sequential, and first you say you have a flattened layer whose input shape is image height, comma, image width, comma, image channel. So 224, comma, 224, comma, 3. And then, so this input shape will be flattened into whatever the product of those three numbers are. And then you have a fully connected dense layer where the number of nodes is equal to the length of this class names array. Class names array had a length of 5. It had elements, it had 5 string values, right? And the activation we are using at the very end is softmax. Before that, there is no activation function. And then in the model.compile function, we also mentioned a few more things. What is the optimizer that we are using? So optimization is Adam. So this is optimizer is used in gradient descent. So there is vanilla gradient descent, there is stochastic gradient descent, there is momentum-based gradient descent, there is root mean square propagation, and there is also Adam. So Adam is one way in which you can make gradient descent process, which optimizes the weights of your model much easier. Let's not go into the details of the Adam. But let's just understand that it's a way to make your gradient descent process much more efficient. And then we have loss function. Loss function defines how far away your model's predictions are from the reality. So here for loss function, you are using categorical cross entropy loss. So cross entropy loss is nothing but, so let's say you have five flowers, right? 1, 2, 3, 4, 5 flower types. Now this could be represented as 1, 0, 0, 0, 0. This could be represented as 0, 1, 0, 0, 0. This will be 0, 0, 1, 0, 0. So these are called as one hot encoding, where the 1 corresponds to whatever that label is and 0 corresponds to the rest of the items. So this is 1 like this, and the last one is 0, 0, 0, 0, 1. Okay. Now, let's say you are supposed to predict that the current flower is whatever the flower corresponding to 1 is. I think it's Daisy. But let's say your softmax predicts something like 0.9, then 0.1, or let's say 0.05, 0.05, then again 0.05 and 0.05. So some of these numbers are 1, right? Some of these two will be 0.1. Actually, this can be 0.025, so that you have sum equal to 1. Anyways, I hope you get the idea. So basically, you sum all these things, you get sum equal to 1. So now, this is a good prediction, by the way, because you are saying 90% chance is there that this is a daisy flower. Now, how do you capture that goodness of this prediction? That goodness is captured using this cross entropy loss. So cross entropy loss formula is nothing but minus sigma yi log to the base 2 of pi. So yi is the actual class of the image and pi is the prediction. So if you are looking at Daisy, then here I equal to 1 to 5. So if you are looking at the flower where it's actually Daisy, it means when I equal to 1, yi cap, which is the actual the value, the actual label, it is 1. But for all other values, it is 0, which means the cross entropy loss will simply become minus 1 times log to the base 2 of 0.9. So it will be minus log 0.9. So this will be the cross entropy loss. This will be a positive number because logarithm of a number less than 1 will be negative. And with a negative of negative, you have positive number. So this is the cross entropy loss that we are using here. And metric that we are following is the accuracy, the classification accuracy, right? So that is the flattened layer and dense layer. All right. So now what we can do is let us copy paste this code and let's just execute it also. So from TensorFlow, we are importing Keras, and then we are defining sequentially 2 layers, the flattened layer and the dense fully connected layer. So we ran that, but we have not trained the neural network yet. So the neural network training is yet to come. So just a quick digression, Keras, as I mentioned, it's an open source deep learning library in Python, which allows you to use TensorFlow framework much more easily. So Keras makes usage of TensorFlow easy. That's all in short. If you are using TensorFlow, very likely you will also be using Keras. And maybe you have already used it if you have worked on neural networks before. Now we'll train the neural network linear model. So optimizer, as I mentioned, Adam, loss function is cross entropy, evaluation metric is accuracy. Now here we have one more parameter called as epochs. So epoch is also like a hyperparameter. So basically epochs means you are going through the dataset 10 loops. And here we are also storing the history of the fit that we are making during the training. And we are also performing validation using the validation dataset. So here to the model training process, we are passing the training data. As validation dataset, we are passing the eval dataset. And where is that defined? That is defined in the very beginning. If you remember here, eval dataset we defined using eval set.csv file as the input, and training dataset we defined using train set.csv as the input. So this is the training dataset that we are passing into this function here, model.fit train dataset, and eval dataset is passed as the parameter to this function. Number of epochs, which we define as 10, we can define it to be 20, 30, whatever, and that we are passing here into this epoch parameter to this function. And we are storing it in this history. Now, this epochs, you can see that initially, did you notice where the accuracy started from? It started approximately from 0.2. And why? Because initially the model is completely untrained. which means the classification accuracy, see, it's very, very close to 0.2, which means the model is so bad in the beginning that it's simply making as if it's making a random classification. And this has to become better as you are going through epochs after epochs, batch after batch of images in the training process. Now, the question that we should be asking here is not whether this accuracy will become 100% or not, because that is very unlikely, right? Because a linear model is a very bad model. But the question is, how much better than 20% can this become? Training accuracy, yes, training accuracy, of course, it should increase, but we're also looking at validation accuracy, because if training accuracy is very high and validation accuracy is very low, it means you have an overtrained model, a model who has kind of rote memorized the patterns in the training data, but it has no idea what it should predict if there is a new unseen data. So the question is how much this accuracy is going to improve. So let this code run. It will take some time for this code to run. Actually, it will take a few minutes, in fact. And once this execution of all the 10 epochs are finished, we'll come back and we'll analyze the results a little bit. So here actually execution was taking some time. So I restricted the number of epochs to 5 for the time being. You can of course execute the 10 epochs by waiting a little bit. But here I just wanted to show you the evolution of accuracy or evolution of losses as we progressed epoch after epoch. So after the first epoch, it was 0.29, not so bigger than 0.2. Then it improved to 0.42, like 42% accuracy, 45% accuracy, and finally it was close to 48% accuracy. So even if you run for 10 epochs, I think generally your accuracy range will be 45 to 55%, somewhere around that range. It depends on, you won't get the exact accuracy always because you are initializing the model with different random parameters. But this is what you should notice. And the loss is decreasing from 23 all the way till 10 or something, 10, 11, the loss is decreasing. But look at validation accuracy. So validation accuracy is definitely below the training accuracy. So this is training accuracy, 29% is going till 48%. Validation accuracy is going from, again, around 28 to 29% till 41%. So not as high as training, but this is what we get. So we can also actually plot this accuracy as a function of epoch or loss as a function of epoch. So this is the plot that we get when we plot training loss or validation loss as a function of epoch. The loss is slightly slowly decreasing. It depends really on your execution, right? You won't get the exact same plot, but generally you will get the similar trend. And here you can see the training accuracy versus validation accuracy. Training accuracy for me, it's close to 55%. Validation accuracy is close to 40%. So I would say it is much better than a random classification. It's not 0.2, it is like 0.4. So twice as better in that sense, but still not as good as what a model can do these days. These convolutional neural network models with deep layers with non-linear activation function can definitely perform very well in these images. These are not at all difficult images to classify. So to plot the training loss and validation loss, you can run this piece of code, history of loss and history of validation loss, and then label should be training loss and validation loss. So this is the loss plot, the first set of this PLT. So here we are using the matplotlib library for plotting. And here this PLT, this plot is basically the accuracy plot. So you can run this also. So I'm copying and pasting this I have copied and pasted this in the Google Colab code. And so here, this is the iteration that is still running for 10 epochs. So it's taking a while. That's why I showed you the 5 epoch code, the results from the 5 epoch code. But I can paste the code for plotting the history of losses here, and you can run it once this finishes execution. So let me just keep it running. And yeah, now let us make some predictions on some sample data. This is the best part of our neural network training. Basically, okay, I have a trained neural network which claims to have 40% validation loss. So if I make 10 predictions, does it mean that around 4 images in the validation data sets will I get a correct prediction? Hopefully, right? That is what the validation accuracy means. So here, this is again a plot of prediction. So we are importing NumPy, matplotlib, and math here for calculating the label, number of the label corresponding to prediction. So here we are iterating to the eval dataset. We are taking the first batch and we are going through different images in the first batch. Then we say the batch predictions equal to model.predict. And by the way, what is this model? Model is defined here. History equal to model.fit, and model was defined as sequential here. Model equal to keras.sequential. So this is the model. So dot fit function is defined using keras in the model itself. So you can call the dot fit function to make predictions on the validation dataset first batch. So that is what is going here. Not fit, sorry, model.predict. Dot fit is while training. So model.predict on the images in the first batch. Then predicted indices are indices from 0 to 4. So that will be the batch predictions for this 16 images in the first batch. And here we are calculating the number of images that we have, which are 16, so that you can display accordingly in the matplotlib subplot. So you have 4 columns and 4 rows. So it will be a 4x4 grid. And so here we are plotting the subplot and we are displaying the images. So this part is very easy. I don't want to go through the detailed line by line code of matplotlib because this is that will become very redundant. This you will naturally learn if you don't know some of the details here. You will naturally learn by using this again and again. But the more important thing for you to realize here is what we are doing here. What we are doing here is plotting the predictions for our images for different flower images in the first batch. So when we run the code, we will see something like this. So these are the predictions that were made on the first batch of 16 images, 4x4 grid. So you can see the number of predictions that we got correct. So what is 40% of 16? 0.4 multiplied by 16 is 6.4. So roughly 6 to 7 images should be correct and remaining should be wrong. I mean, I would not be surprised if we get more images correct, but that's kind of the expectation. So let's see how many images have been predicted correctly. So here prediction is sunflower, actual is sunflower. This is correct prediction. So let's put a tick mark. So this is correct. Prediction is sunflowers, actual is sunflowers. This is correct. Prediction is dandelion while it's actually sunflower. So this is wrong. This is correct. This is correct. This is correct. This is correct. Tulips. This is correct. So how many did we get correct? 1, 2, 3, 4, 5, 6, 7. See, we got 7 images predicted correctly. The rest of them are wrong. Oh, this is also correct, by the way. So 8 of them are correct. Rest of them are wrong out of 16. So here in this batch, the validation accuracy is, I would say 50% because out of 16, 8 of them are correct. But for many other batches, it might be, for many other batches, it could be 30%, 35, 40%. So on an average, your validation accuracy score is 40, 41%. So it's beautiful, right? Basically, what your model says it will do, you are able to visualize it here. Here in the red box, actually, I had denoted the flowers where wrong predictions were made. So in fact, this was also wrong prediction. So I should put a red box around this one also. This guy missed my vision when I was marking the wrong predictions in this red box. Anyways, so this is how you can make the prediction. So I am going to, while this code is running for 10 epochs, I'll also copy paste the code for making the predictions. So this is the code for making the predictions. And let us paste it here. And as you can see, this code has been running for some time now. So for like 5, 6, or maybe more than that, maybe close to 10 minutes, this 10 epochs have been running. And we have so far only finished 2 epochs. So there are 8 more epochs remaining. So this is why I reduced the number of epochs to 5. You can try one more thing. You can try running with the GPU access on and see if this training is faster. I'm sure it will be faster, but I haven't switched on the GPU right now in Google Colab. So this is basically what you get by using a shallow neural network with no linear activation function, except at the output you are using softmax, but also no convolution operation. Did you see convolution anywhere? The convolution filter and all we discussed in the last lecture, did you see that being used anywhere? No, it's not used. So the reason why 40% is the validation accuracy is simply because of that. Purely linear model which cannot learn any nonlinear pattern. But still, I am actually personally surprised that this model works this much, 40-50% accuracy. It's bad, but still better than a random classification. But yes, we need sophisticated convolution operation to make this better. So that is exactly what I want to discuss in the last 5 minutes of today's lecture. What can we do to improve the model accuracy here? Use deeper network, use more hidden layers, basically. Use non-linear activation like sigmoid or ReLU, rectified linear unit. You can use that in some of the layers, and then use convolutional neural network. So in the subsequent lectures, we'll be introducing deeper layers, activation, nonlinear activation functions, and convolution operation as well, to make our predictions better. And we will see how the predictions are improving compared to this linear model. Deep versus shallow neural network, we already discussed in the starting of this lecture. But activation function, basically, these are some famous activation functions where if your input is linear, if input is like y equal to x, this converts, sigmoid converts y equal to x into 1 by 1 minus e raised to 1 by 1 plus e raised to minus x. Tan hyperbolic is also like that, whose range is from -1 to 1. Sigmoid is from 0 to 1. ReLU, rectified linear unit, converts the inputs to 0 if they are negative numbers. Otherwise, it is preserved as such. Leaky ReLU will not convert to 0, but it will convert it into a scaled down number. So this A can be 0.1. So basically, if the input is -10, output will be -1. So that is called leaky ReLU. These are all famous activation functions. So we'll see the usage of some activation functions like sigmoid and ReLU in the subsequent lectures, and of course, enabling deeper neural networks for actual deep learning of the features. And convolution operation, we have discussed in detail in the last lecture, but this is convolution in a nutshell, right? So you have a kernel or a filter traversing along the images. So here, if the kernel is defined such that its shape is supposed to capture the shape of a human eye, then when the kernel reaches this eye, you can see that the output, which is this, is maximized when the kernel is, let me play this once again. Yeah, see, just notice that the output is close to 0 when there is no overlap between the pattern in the kernel and the pattern in the image. But when the pattern in the kernel and that in the image is overlapping, you saw that in this matrix, the output was maximized. It was close to 100. This is an oversimplified version of convolution operation, but in essence, this is exactly what happens. This is also a simplified version of convolution operation in a GIF format. So you have a kernel moving across the filters. Across the matrix, this filter is moving, and then you have an output. We have discussed in detail about how the convolution operation and filters work in the previous lecture. So if you haven't covered it yet, just go back and have a look at it. It will give you a fairly good idea about the convolution operation. So that kind of brings us to the end of today's lecture. But let me take just 1 minute to congratulate you for finishing this yet another small step in this journey of learning computer vision from scratch. You are kind of here, right? Counting from the lecture 0, you have finished 4 lectures now. But this is not our goal yet. Our goal is to finish the entire series, which may have around 35 lectures. But nevertheless, let us feel proud that we have reached here. Let us congratulate ourselves for the consistency that we have maintained, for the discipline that we have maintained. So if you have finished the lecture, I really appreciate you. I wish to meet you again in the next lecture. I hope you are taking down notes. I hope you are running the code along with when I'm running the code. I hope you are going through the extra materials which I'm posting. So in the link, and please go through that. Please read our Substack article. And with that, let us wind up today's lecture. We'll meet again in the next lecture, where we'll be working on a deep neural network for classifying the same set of images, and we will see how it is better than the current linear shallow network that we defined. So thank you so much. Take care and bye.